Okay, good morning again, guys, and welcome to Physics 252. You just came from Physics 251. Before that, you did 250. This is the last sequence in Physics 250 series. My name is Bouzidi Jumoui, and I go by DJ, by the way. I have a PhD in physics from the University of California, San Diego. I taught physics in Crafton. I taught all of the sequences actually, including 250, 251, 252. And I also taught physics 100, astronomy. So I taught a lot of things in Crafton. This is probably going to be my last class for Crafton because I'm moving somewhere else. Anyway, the class itself is modern physics. This is a calc-based class. And it's very intensive stuff, so I'm hoping that you guys have no difficulty with this one. And my PhD actually is in theoretical physics, which means that I can do math. So that's really what it's supposed to mean, okay? So we'll have extensive use of mathematics in this class, so you really have to be ready for it. This class is divided into two main topics, okay? The first one is thermodynamics. And with thermodynamics, we're going to discover the three laws of thermodynamics. The first one is the Zeroth Law. That's what chapter 17 is. Then we're going to discover the first law of thermodynamics. And then the second law of thermodynamics. So what are these laws? First, historically, these laws were discovered backward. The second law of thermodynamics was discovered first by a question that Mr. Carnot has asked. Mr. Carnot was an engineer in the French army, basically working on the railroad at that time. And he asked a simple question: what is the most efficient engine? That's all the question he asked. He was working on the railroad. So he wanted to see, can I build an engine, for example, instead of using water, maybe I should boil, which has different boiling points than water. Could that make a difference? Could I have a more efficient engine than that I thought of? Maybe instead of having the chamber made out of iron, maybe I can make it out of aluminum, different physical properties, for example, for thermal conductivity or something that could impact that. So that's the question he asked. In doing so, he discovered the principle. And the principle is very simple, actually. It says the following: if I have a hot source and a cold source, heat will always flow from the hot source to the cold source. That is something that you can experience on a daily basis. Take a cup of water that is boiling and put it in a room where the temperature is room temperature, and wait a while. Monitor the temperature, and you will see that the temperature of the boiling water will start to drop. If you pay attention and you do very detailed experiment, you will see actually that the room temperature will increase, provided that the room is small and you're not actually dealing with a heat sink. So that was the principle that he discovered. And people thought that he was onto something. Then he said, okay, grant me this, which is what he stated as the law, then later on stated as the second law of thermodynamics. Then I can show you what is the most efficient engine. That was in what, 1826 or 1825 or something like that? That was a long, long time ago. Not a single person until today could come up with a more efficient engine than Carnot. It is the most efficient engine. And we have people working in Toyota, and I own a Prius, which means supposed to be a very efficient car, and there are other better ones than that. There is the Tesla and other people who have cars that are supposed to be more proficient in terms of energy, yet they still cannot beat Carnot cycle engine. You will learn later on that it's actually a theoretical engine and not a real. You cannot make it in real life. There is actually another engine that I have in here, which comes as close as possible from Carnot cycle. And this is actually the Stirling engine, goes by the Stirling cycle. This is actually a very good engine if we can make it. Still, we can make toys out of it. I have actually several versions of it. And at some point, we're probably going to demo this one in here. And I have yet another version of it that can work with ice. And if this is not enough, I have actually a fourth version of the engine. You can grab it from here. By the way, my desk is a mess, okay, for a reason. So this is actually the Stirling engine, which you can go and buy from Amazon. Okay, that's what I get all of my engines in the end. And it's still not as efficient as the Carnot cycle, but it is very good efficient engine, but we don't use those. We use the diesel engine, which uses the diesel cycle due to Mr. Diesel who invented it. And we use the auto engine, OTTO engine for cars, which is also used in cars. Okay, and we use other kinds of cycles and processes to make engines. We're going to learn about these things, but then people discovered that, you know what, this law is wonderful. And Mr. Carnot was on a very good point. So instead, they thought that this should not be really the first law of this branch of science that is emerging. They decided that it should be the second law, because before it, there is the law of conservation of energy. So they moved it. It was discovered first. They moved it to second. And then about 20 years later or so, they came up with the first law, which is really the conservation of energy, which wasn't known before, but they put it in a formal way. They put it in a formal fashion that this is the first law and this is the second law. Well, way after that, okay, when this thing started to get a hold of itself and becoming a really solid science, then they said, you know what, we really need a law before the first law. And that is, how do we know the temperature? What is the temperature? How can we measure temperature? And that is when they said, actually, we need the law first to define the temperature, which will allow us to invent, among other things, the thermometer. Once we have a thermometer, then we can talk about temperature, we can talk about the first law and second law. Of course, at that time, the first law and second law were already well established. So the zeroth law was called zeroth for this reason, so that it comes before one, and so that things are not moved along. You see, this branch of science was discovered backward, and it was discovered by an engineer, by the way, not by a physicist or a scientist, okay? And it's a very, very powerful branch of science. This actually has applications everywhere. Physics, chemistry for sure. No chemical reaction can happen unless it obeys this law, this branch of thermodynamics. So if you're going to go to become a chemical engineer, you cannot really do it without thermodynamics. Also, any kind of engineering, society in general, economy in general is governed by this thing. As a matter of fact, the entire fate of the universe is determined by these laws. As a matter of fact, there seems to be a correlation between the second law and the flow of time. I mean, I remember yesterday, and I'm sure you do, and we remember the past, but we cannot remember tomorrow because of the second law of thermodynamics. It seems like it's putting a lot of constraints on us, okay? So that's why it's a very powerful thing. One of the questions that was raised actually, and was really debated big time, is when we were talking about the black holes, and black holes seems to absorb everything in them. So what happened to the energy? That was a big problem. Is the energy conserved inside the black hole? Of course, you can prove that it is. It's not hard to do so. But the problem was the second law of thermodynamics. Is it violated just at the boundary of the black hole? And that was a big debate until Mr. Hawking came up with a solution to the problem and basically showed that the information, namely the entropy, is not lost, and it stays on the surface of the black hole, which is a big topic, a big deal, which really prompts other physicists later on to work on the so-called hologram theory. Are we really living in a three-dimensional universe, or are we living in a two-dimensional universe? In other words, what you see before you as depth, height, and width, is it real, or is it your basically reality is made up in front of you? This is not sci-fi, by the way. This is real science. Physicists are working on this problem, trying to resolve it. This is called the hologram theory. So this stuff is, where is it coming? from this branch of science. So it's very, very important. Thermodynamics, I cannot emphasize how important it is. As a matter of fact, some people, they use it for religious purposes and philosophy, of whether or not the metaphysical exists or not, whether or not God exists or not. So there are all kinds of things. So it's really a big deal, okay? I really encourage you to read the story by Robert Heinlein about the, is it him or somebody? No, actually it's not. It's the one who wrote Foundations, this Foundation series. I forgot the name of the author. Isaac Asimov, okay? About the last question. It's really fascinating stuff. And again, it's coming from the second law of thermodynamics. So it's important stuff, not just, it's important for us, first of all, for physics 252, so that we pass the class, okay? We have to get to know all of these things and do them and do the calculations and how to calculate the energy and how to calculate the heat and how to calculate for different processes, the processes that we're going to be talking about, namely the isothermal process at constant temperature, isochoric process, the process at constant volume, isobaric process, the process at constant pressure, and adiabatic process, the process where there is no heat exchange. And combine these ones in here and do calculations, trying to find the work that is involved, the heat that is exchanged, the efficiency of the engine, or the factor for the, if it's not a heat engine, but rather it's a heat pump, namely an AC unit, how to calculate the different properties of the systems. This chapter 17, 18, 19, and 20, exam 1, okay? So by then we would have mastered this stuff. Then we jump into exams 2 stuff. So we're gonna skip a bunch of chapters that you guys covered in physics 2 or physics 251, and then move on to chapter 37, which is relativity. Again, there are 2 types of relativity. There is the special theory of relativity, which we're going to cover. And then there is the general theory of relativity, which we're going to barely touch upon when we're doing elementary particles later on. So the focus is going to be on the special theory of relativity and the postulates for it. And we'll try to justify why do we need that. After all, we had a wonderful theory by Mr. Newton. What was the main thing that you learned from physics 250? Do you guys remember? What's the main thing? What stands out from physics 250? I know it's a long time ago, and probably if I ask you what did you have for dinner yesterday, you forgot. But there must be something that is more important than your dinner last night and more important than everything else. You remember? Take a guess.
It's in Newton's 3 laws.
3 laws. That's a good answer. That's the best answer, actually. That's the correct answer.
Oh.
Anything you have learned, it's the second law, really. F equals to ma. Does this ring a bell now?
Yeah.
Everybody else? Never forget it, okay? Never forget F equals to ma. It's probably the most important thing that you should remember from physics completely. F equals to ma. And it's a great thing, okay? By the way, what did you learn from physics 251, I'm sorry. What was the main thing? We learned F equals to ma. That's great from physics 250, which is a big equation, which is 3 equations, by the way, because it's a vector relationship, which means it has an x component, a y component, a z component. So you learn 3 equations, really. For 251, do you guys remember? Okay, let me share with you the screen, first of all, because it's a bunch of things that I'm sure you learned. And let me open a new tab, completely new. Let's call this one 252. And let me share the screen now. Share. We're still in the intro, by the way, okay? Does everybody look at something that says 252 F21?
Yes.
Yeah, very good. So 251, 250 first is easy. It's not easy, really. You spend a lot of time doing the projectiles and doing the work energy theorem, and you're doing all kinds of problems involving the Atwood machine and all kinds of things, okay? So it was not really easy, but it was a lot of fun. I hope that you guys enjoyed it. This is what you really have learned, correct? That's really the equation that you work with. Let me write the equations that you must have learned in physics 252. The first equation was Gauss's law, and correct me if I'm wrong, okay? That talks about the divergence of the electric field being really proportional to the charges that created them. In other words, the electric field is created by the charge distributions. I'm writing it in a differential form. Probably you've known it in the integral form, which states that the flux of the electric field over the closed surface is equal to the charge enclosed divided by epsilon naught. Is this, it's the same equation, by the way. Yes or no? Does this ring a bell? Okay, so this is equation number one. This is one equation because this is a scalar, actually. It's just a scalar product of two vectors. This is the operator that is basically take the derivative with respect to x in the I hat direction with respect to y. I know I'm writing these things hoping that you guys remember them. If not, this is a refresher for what we just did in physics. So 251, yes? I'm kind of lost. I usually like to see the faces to see if you guys are okay with it or not. Sounds good? Okay, at least one person is nodding. That's good. So this is the flux of the electric field is equal to the charge enclosed divided by epsilon naught. That tells me the electric field is actually produced by the charges enclosed. So if there are no charges, there is no electric field. That is Gauss's law, okay? Both in the differential form and actually the integral form. And this is something that is one equation. It doesn't tell me the entire story of the electromagnetic field, just tell me part of it. The second thing that you've learned also is that the fact that the divergence of the magnetic field is zero. And that tells me that the magnetic field does not come in monopoles. You can only have a north pole and south pole together. You cannot, no matter what you do to a magnet, you cannot isolate the north pole from the south pole. It's always together. So if you cut it somewhere, you're going to end up with a north pole and south pole still, which means that the divergence, and like the divergence of the electric field, which could be non-zero because of the fact that you could isolate charges and you could have charge distribution. So the divergence of the electric field is not necessarily zero, but that of the magnetic field is always zero, because if I have a magnet, the field that emanates from the north pole will always terminate in the south pole, no matter what. And because the integral of the flux over a closed path really is a measure of how many fields come in and out. So the number of fields that come in is the same number of the fields that come out. So the total is zero. So that was the second equation that you learned. So this is equation number 2 from physics 251. Does this ring a bell?
Yes.
Okay, very good. So the third equation that you learned was a little bit more, and actually I'm going to put them out of order. You learned the third equation third, I'm going to put them out of order. So I'm going to put the fourth equation first, okay, which is really Faradays law. Faradays law says that basically the circulation of the electric field over closed path is proportional, or is equal actually, to the rate at which the flux of the magnetic field is changing with time, where phi b is defined as the integral over the surface that is enclosed by this path. This is a closed integral of b dA. Don't confuse this sum, of course, I'm sure you did that, with this sum, because this is a closed surface and this is an open surface. That's the difference between that. So this is not necessarily zero. So if I take a magnet and move it up and down in a region, so the magnetic field lines could be increasing or decreasing, depending on how I'm doing it, then there is a current that is going to be induced in the loop. Okay? And this is the magnetic induction of the electric field. So there is an electric field that seems to be generated in here for the charge to move in this conductor. You did the law of induction, didn't you? Faradays Law. Yes. I know the summer went out and you probably forgot a lot of these things, but this is basically Faradays Law, which can be written in a differential form also in the following fashion, as the curl of the electric field is equal to minus the derivative with respect to time of the magnetic field. Now you have to remember that this is because this electric field is going around in a loop, so it's curling. So that's its curl, and its curl is equal to how fast the magnetic field is changing. It's proportional to the rate at which the magnetic field is changing in and out of that surface that is enclosed by that loop. Okay? So, and the sign for it, the negative sign is due to Mr. Lenz, and Mr. Lenz basically said that this change has to be correct because this is actually a resistive effect. Okay? So this is Faradays law, and actually this is, I put it as equation number 3, but actually in the book, the way you learned it is equation number 4. And it's actually not one equation, this is actually a vector relationship, because the curl will give me 3 components in the x and y and z direction, and this actually is the derivative of the magnetic field, which is also a vector that has x and y and z components. This is actually, and inside of it, there are 3 equations, just like this law that you learned in physics 250. This is actually 3 equations, not just 1. Okay, so this is similar to it. And the last law that you learned is Ampere-Lenz law. Ampere-Lenz law tells you basically that what causes the magnetic field is actually the current that is enclosed. And Mr. Maxwell fixed it in a sense that he said that, you know what, there is a displacement current. He called it the displacement current, and he actually believed that it was a current, where this is basically how much this is equal to, where the flux of the electric field now is. Instead of the flux of the magnetic field, we're going to use the flux of the electric field. So this is correction done to Mr. Maxwell. This is what Mr. Ampere has proved. And of course, you can write this expression. Again, you came to a region in space where there is actually current flowing. So this is a current that is flowing, and you go around it, and you measure the magnetic field and how it's going to circulate in here. So this is B actually, and it's going to circulate due to the electric current that is enclosed by the path where you're trying to measure the flux of the magnetic field. No, not the flux, the circulation, I'm sorry. This is the circulation of the flux, okay? And again, if you write it in a differential form, this looks like this. The curl of the magnetic field is equal to, proportional to the current density, plus mu naught epsilon naught, the derivative of E in this case with respect to time. So this is actually also equation number 3 corrected with this term of Maxwell, but this also has 3 equations inside, because this is actually a vector relationship. This is actually a current density, which is also a vector, okay? So this is the stuff that you learned in physics, in addition to Lorentz force, and Lorentz force says that a charge that is sitting in an electric field will experience a force, and if it's moving inside the magnetic field will also experience a force that is proportional to the charge and also perpendicular to V and B, but also proportional to their values and also the direction, the angle they make between one another. So this is the Lorentz force. And this too is actually 3 equations, because it's actually it's actually a vector relationship. So you should have 3 plus 1, that's 4, plus 1, that's 5, plus 3, that's 8, plus 3, that's 11 equations. 11 equations versus 3 from physics 250. So this is only to physics 250. okay? 11 plus this one, because the ultimate thing, once you find the force, you go back into physics 250 and solve for F equal to ma. It's a lot of things that you did in physics 251, isn't it? According to Mr. Feynman, and by the way, I always list Mr. Feynman's lectures as one of the resources I use, and I'm going to give you the link for the lectures, which are free lectures, free textbook to use. This is all the knowledge prior to Mr. This is all you need to know in physics before Mr. Einstein. The things you learned in physics 250 and the things that you learned in physics 251 are good enough. You can even solve thermodynamics problems. And actually, we're going to use F equals to ma to solve thermodynamics. Stuff from physics 250 is going to be enough to do thermodynamics. We don't need even the stuff from 251. So everything we know in physics is based on these equations, actually. These are called Maxwell's equations, including Lorentz force, by the way. And this is Newton's second law of motion, which is really a summary of everything from physics 250, classical mechanics. Up to that point, everything was looking good, but then there started to appear problems. Okay? Then things started to violate things. One of them is an experiment by Michelson and Morley, because one of the problems, one of the solutions of these equations actually was what you did in chapter 36 for the EM waves, the electromagnetic waves, which is solution to Maxwell's equations, and shows that light is actually a wave. And it's a wave that travels with a speed, c, that is 300 million meters per second, roughly. Okay, that's the speed that you found. It's a tremendous speed for a wave to be traveling with. If you remember from physics, what is it, 250? Did you do sound in 250? Yeah, we did sound in 250, no? Sound waves. Okay. So then you remember basically that this is a this is tremendous velocity, by the way. This is a lot of velocity for a wave. That means that the medium that it's traveling in, which is where it's supposed to travel, where light is traveling, must be a very stiff material, extremely stiff, meaning that the material that is, because between us and the sun, we must have that material. And between us and the next star or any star that we see at night, we must have that material. It has a tremendous stiffness, spring constant if it's a spring, if you like to call it spring. And that is what the hypothesis for the ether was formulated. So Mr. Michelson and at that time Morley, they decided to do an experiment to determine how fast the Earth is moving around. I mean, how fast we're moving in this medium, which they call the ether. So what they did, they did observation. They put their apparatus in one way and decided we can find how fast it is because we know how the Earth is moving around the sun. We can find that is. And then they discovered no velocity because they said, okay, maybe this is the day when the Earth is actually moving in the same speed as the ether. So if we look at it in the opposite direction, 6 months from now, when the Earth is moving in the opposite direction, then we're going to find how fast the Earth is moving with respect to ether. No matter which way they orient their apparatus, they found no mention whatsoever of the ether. It took the genius of Mr. Einstein to look at these equations and said that these equations are valid everywhere. They are valid in vacuum, as a matter of fact. So there is no need for the ether with that tremendous stiffness. And the experiment showed so. So he had to reformulate classical mechanics and making the assumption that light travels with the same speed everywhere for all observers, basically. From that simple postulate, okay? And the postulate that all observers must experience the same physics regardless of how fast they're moving with respect to one another, whether you drop the ball here or you drop it on a train moving at constant speed, they should accelerate toward the ground with the same velocity, with Both observers will do the same measurement, and we'll find how fast the ball is going to drop after 1 second, basically. Those two postulates are good enough to come up with a brand new physics. Brand new physics. Isn't this amazing? Everything that you learned so far, at least in terms of classical mechanics, will be abandoned. And you come up with something new from chapter 37, just with these two postulates. And of course, that new thing must include the stuff you learned in physics 250. Whatever we come up with should not, because those are experiments. The Atwood machine, for example, and the stuff that the incline, for example, and dropping a mass coming on the incline should be repeated again. Should not, because that's an observation. So under chapter 37, we should not violate that. And then after that, we will move to modern physics. First of all, the classical theory of the atom due to Mr. Niels Bohr. And that should be enough for after we chapter 37, 38, and 39. Enough for the next exam, the second exam. And later on, we introduce quantum mechanics to improve on that, because Niels Bohr model will be insufficient. It's going to apply only to the hydrogen atom. Helium, it doesn't apply to it. Unless you take one of the electrons out and it becomes an ionized helium, which is what is known as a hydrogen-like atom. It's not really a hydrogen, but it's a hydrogen-like atom. If you take lithium, which is the next element in the periodic table, and you remove 2 electrons, and you solve, and then you can describe the system as being a hydrogen-like atom. It's still not really lithium in neutral fashion. So that model for Mr. Niels Bohr was almost close enough, but not good enough. Then we're going to derive Schrodinger's equation, or come up with a formulation for Schrodinger's equation, and build a brand new physics called quantum mechanics that helps us understand the very small. Okay? Understand the very small. The trouble with that is, first of all, it's a wonderful branch of science, quantum mechanics is. At some point, we need to further down go into quantum electrodynamics, where Mr. Feynman and Dirac, they put together even a better model, trying to unify even the photon, bring the photon to the picture, namely electricity, namely physics 251, into the picture. And now they have the most precise theory that you can think of, QED, quantum electrodynamics. There is not a single science that ever invented by mankind that is more precise than QED. When I was taking this class, when I was a graduate student, I was frustrated with the instructor, Professor Bruckner, who was one of the smartest people I have ever met. Yet, he spent a lot of the time using all kinds of approximations, going from the 12th digit after the decimal point to the 13th digit after the decimal point. What a waste of time, I thought at that time. I mean, if somebody gives you an experiment and he's got 3 decimal points, 4 sig figs, that's an excellent result. 5 decimal points, that's actually an outstanding. 6 decimal, 7, and now we're doing the 12th trying to go to the 13th. Why are we doing that? He was a Nobel Prize laureate, and he was actually an outstanding professor. But just to show you how precise this science is, QED is. It's an amazing branch of physics. So we're going to get, unfortunately, we're not going to get into a lot of details because it combines a lot of stuff, but we're going to get into a lot of the fun math that is involved with it, with the fine structure of the electron and then the stuff that has to do with the nucleus and things like that. Then even further than that, we're going to even get into the structure of those elementary particles, namely the proton and the neutron, and see what's inside of them. It turns out to be quarks. And then we get into stuff that is a little bit even more confusing at first, and that is basically the different properties, the different quarks inside, namely with different names that sound kind of strange and charm, and you start to run out of words, basically. And it's just like names, for example, when you're doing physics 251, you were introduced to the concept of a charge. Probably you had never thought about it, what the charge is, but it's just a property, just like the mass, just like these properties that I'm talking about. And you have a positive charge and a negative charge. What's the difference between them? Just names we use. We could have called them up charge and down charge. We could have called them left charge and right charge. We could have called them the Democratic charge and the Republican charge. We could have called them whatever, okay? But the point is, we call them positive and negative. Just because one of them is positive is not any better or worse than the one that is negative. It's just a convention. Same thing when we come to those things, to the quarks. We have an up and down, we have the charm, we have all kinds of the bottom, the top, and we have all kinds of names for them. Please do not start thinking in terms of those adjectives that they have any meaning, just to make a distinction, okay, between them, because they have different properties. And that is another branch of physics actually called the QCD, quantum chromodynamics, okay? Chromo has to grow with color because we have different flavors of things and how to. At that point, we're doing something called the standard model. This is the most up-to-date physics that you can ever think of, the standard model. It's a combination of really QED and QCD and different stuff in there. Unfortunately, and with a very, very basically disappointing and sad thing, physicists from the beginning of the 20th century till today, they were trying to unify these outstanding ideas between relativity and quantum world, and they could not, including Einstein himself. He died, and he was still working on it in 1955. Everybody was still working on this, and it's still. There are some candidate theories out there, but they are not really things that you still can't call of them. And that is the unifying theory, the grand unifying theory of physics. That's what people are trying to work on. The good one probably right now, or at least the one that is a lot of physicists criticize, is the string and superstring theory and all of these things, but it's still really not like the standard model and the other things that you can do calculations and you can actually test them in the laboratory. We're going to use these things at the end, the last chapter, to try to understand the evolution of the universe, trying to understand cosmology in terms of elementary particles. What happened to the universe immediately after the Big Bang? And when we say immediately, it's before 10 to the negative 43 seconds. We're not talking 1 second. 1 second is an eternity at that point after the Big Bang. We're not talking about a millionth of a second. That's still an eternity after that. So we're talking about 10 to the power negative 43 after the evolution of the after the Big Bang, and then we will see what kind of basically how the forces start to break and how the particles start to form until we reach the age of the molecule where we are right now. Okay, which happened just fractions of a second later on. Okay, no, I'm sorry, the molecules happened about 300,000 years after that, but the age of the baryons, the proton and the neutron, came after the universe cooled down, which was a fraction of a second still. So we're going to talk about cosmology in terms of, in relationship to how we can understand in terms of elementary particles. Sounds exciting, doesn't it? At least I am. I don't know about you guys. Yes, no? Or just you want to pass the class? Okay. It's fine if you want to pass the class, okay? Just show me what to do in exam 3 so that I can get an A and done with this thing. That's fine. Hopefully we do both, okay? So again, we're going to be meeting online, okay? We have the materials of the class on there. Now, let me show you the course in here. I know the homework is already on Pearson. I did not really make the assignment. Yes, I need to copy them and clean them from the previous semester. But I'm going to show you basically how the structure of the class is. I'm sure now you're experts in terms of how Canvas works, but I'm going to show you nonetheless how we do things in here. So let me first of all find the link. I'm in student view. Let me just refresh to make sure that I'm still in student view, because sometimes I lose sight of that. Okay. So let me share with you the screen, because you might have had a different understanding with different instructors, and that sometimes can be an issue in here. Usually what happened was when I shared my screen is, I'm talking about something and you guys are looking at something else. Does everybody look where it says physics 252-225 in here?
Yes.
Okay, very good. So that we're on the same page, okay? This is where you most of the time are going to be spending your time in my class, okay? You're going to be on the models page. So when you click on home, like this student, this is a test student, not a real student. This is what you're gonna see, okay? That's where you're gonna be. This is what I want you to really be on a regular basis, day in, day out, okay? This is where you need to be. There is something dangerous in here that is tempting. Do not try it. It says the to do. This is on an emergency basis only. This is really Canvas's way of saying, you know what, there is a red flag in here, okay? You don't want to be raised a red flag. You would want to get a green flag. You would want to be in good standing in here. And for that, you follow these things in here because it has due dates in here and it picks up the due date and it tells you what is coming and what is happening and so on and so forth. Don't worry about this section if you do this one. Of course, you have to do it in time. Of course, in here, the only thing that I can see is this one and this one. Those are the only two. The others are grayed out for me. I cannot do them as a test student. You probably, depending on your case, you may have done already several of them, and some of them already are ready for you to move on. So what we have in here is, first of all, this is models, model 1, and then this is week 1. So this is where we need to be. Before I do that, since we are in here, let me show you the syllabus first of the class. As a student, this is the syllabus of this class. I urge you guys to look at this and try to follow it and make sure you understand everything. If you have any difficulty, please let me know. At some point, probably it's a good idea to have one of these two online tools. I mean, not online tools, electronic tools. If you have a different one to use, it's a good idea because you will have a lab that is very intensive in integrations and stuff like that. And if you have one of these things, it simplifies your life extensively, okay? So that's a really good thing to have because there is a lot of work in here. This is the course this is the homework page basically. And what else? In terms of the grades, here they are. Attendance, it's called attendance, is actually participation. And you will see how participation is graded, okay? And this is the grading policy and this is the stuff. Of course, please be familiar with this page in here because it's fully enforced. Also follow the policies in here. I'm going to talk about that briefly, okay? This is the schedule for at least of the chapters that we're going to cover. I'm going to try to stick to this one as much as possible unless there is any unforeseen reason or if there are some changes that we need to make, I'm going to let you know about it. The final is scheduled on sorry, it's December 14th, okay? Sorry about that, okay? And these are basically something that I want you to have your attention to. So let me go into, this is basically the printed version if you want to print the syllabus so that you guys can look at it, okay? And let me go into the home again. Let me look at these rules again. It's the same thing that is on the syllabus, by the way. This is the stuff that you really have to do, okay? You have to agree to it. And you have to mark done in here. If I see it's not marked done, that means I assume that you're not agreeing with this rules and how to communicate online with each other, or you don't agree with this handbook, in which case we have to stop everything in here, okay? So I really have you to have mark it done. If you don't mark it done, I assume that you're not basically adhering to all of these things. So what this is saying basically in a nutshell is the following. You are in an online environment, and I'm sure since this is 252, this is not the first time, but at least I want to emphasize this point in here. You are in an online environment, so sometimes we lose sight of the fact that we're dealing with people. We think that we're dealing with a monitor and a name attached to the monitor, and a name on the monitor. So, but there are real people on the other side. In real life, we're meeting, if we are meeting on campus or if we're meeting in the lab, we can see each other. I mean, I can, just from the expression on your face, your peer can understand if you were joking or you were serious. If from a gesture of your hand, that can also tell something else. So people can read that, and it's a helpful thing to communicate your point. But online, you really lose those things. And sometimes you're writing something and you have a very good point trying to raise. But when you look at it, you say, oh man, it doesn't sound right. Okay? That is the time when you decide to read it again. Read it to yourself. If it's good, if you think it's good, then it's fine. If you think maybe there is something, that is when the time you read it out loud and put yourself in the shoes of the other person who's going to receive or going to read your post. If you think that it's still coming too strong or maybe coming a little bit off, that is the time when you have to really reword it. As I was saying, you may have a very good point, and we don't want to lose that point, but maybe the wording needs to be slightly changed. Okay? Because you have to be mindful of the fact that there are people on the other side who may not interpret what you wrote the way that you intended. Does this make sense? Okay, so if we agree to this, then I'm going to mark it as done. If I see this, that means that you're in good shape. Then I'm going to move next. Okay, this is a must. Okay, otherwise we cannot. I'm trying to move in here. I'm a test student, of course. If I try to move, it tells me that you must complete this thing. Okay, please do your best in it. I don't expect you to get in the whole thing. Remember, it's not going to go into your grade book at all, so it's not going to impact your grade. Okay, but it's just to help me basically see where you are. It's actually a college basically where they want this to be done. Okay, so let me go back into the home in here as a student again. So the things I need to do is here. Then today's meeting is going to be posted in here, the link for it. There is a link from before. If you find it useful, you can watch it. If not, today's meeting is going to be posted in there. There will be tasks to be done on every meeting. And you need to come to the replies in there. And this is a discussion item, actually. Okay. It says in here, week 1 discussion. I'm sorry. It's this one. I'm sorry about this one. So the week 1 discussion is the one that I'm talking about. It has 5 points. So you will have an item of discussion there. And it's worth 5 points. That's where you come in and you reply. It's not a challenge. It's something that you should be able to do, and we can even do it in the classroom. So it's not like a homework where you're going to research stuff or anything like that. If you attended live, you shouldn't have any difficulty whatsoever to doing this one. If you cannot make it live because you have other things to do, or you have a meeting, or you have other class, or you have other business, that's fine. You need to watch the recording of this semester session, not the one from previous, and actually reply again accordingly, and you should have the full mark for it. It could be 1 item to do, it could be 2, it could be 3, and so on and so forth. We're going to be meeting on a weekly basis every Tuesday, same time, for sure. And also we have the potential to meet on Thursday and Friday, Thursday for both sessions, depending. I'm available during that time, those times, and we can basically have those meetings if need be. The purpose of the Tuesday meeting is to get us started. This is an online course, because when I structured it in the past where we have regular meetings, people complained, they said that it's an online class and why you're forcing us to be there. We can basically take it at our pace. So this is like a solution in between, okay? So we can do this, and then we get us going. We discuss the important things. We do even examples from the book, problems from the book. We solve them, and then you come in later on. And sometimes I start solving the problem. Right when I set it up, I tell you, you guys finish it and put it in the discussion item. Okay? So that shows me that you're actually doing the work you're supposed to be doing. Okay? And if there is a homework problem, for example, that is too hard to do, and there is one actually that I noticed in the past that was very difficult to do, we can come in here and discuss a solution for it again. And then you can go back to Pearson and finish it. And if it's a question related to it, put the numbers in, because most of the times I don't do the numbers unless I need them. Then you're going to do that in the discussion. You're going to get full credit for it. If you don't do this, if we don't have regular meetings, and if you don't follow and participate in the class, things start to pile up. By the time it's an exam, you have an overwhelming material, and you will have very hard time trying to keep up with the class. Okay? In which case, your grade could suffer, or you may drop out of the class completely. So this is actually a check on a weekly basis to make sure that we are on task. Does this sound like it's a good plan? Okay, very good. So this is graded, and you have to understand that you cannot bypass this step. You cannot not attend live, and you cannot watch the video. One of the two must be done, if not both, if you want to, okay? Because you cannot come to the discussion and look and say, you know what, I really don't want to watch. I'm too busy anyway, and I have a game to go and watch or play or something. If that's the case, you cannot see what other people have posted unless you yourself post, number one. Number two, you cannot put something in there just to see what other people have posted and edit your post. Because if you edit it, it nullifies it, so don't edit it. If you make a mistake, please let me know. Hey, I know that is, but this is how I meant to do it. That's fine. Or post a reply to yourself so that they can see that you have actually, which can happen, and it did happen in the past, okay? So in other words, you really have to be doing the tasks as they are done on the weekly basis so that to keep up with the work. This is a fully loaded class. It uses a lot of mathematics, requires a lot of attention, requires a lot of reading actually from your part. And hopefully you guys can survive it by the end of the semester. And more than that, hopefully you enjoy it as much as I do enjoy it too, okay? You have a lab in here. I'm going to have another session just dedicated to the lab where I'm going to talk specifically of the lab, because every assignment, you have a quiz for this chapter. Let me turn off the students in here and talk about the lab, because it's important, okay? Because you can't see this one yourself unless you complete it. This lab says that it's over 53 points. How much I'm going to get for this lab. If I write my name on the lab report, which is in here, I get 1 point for it. If I don't include my name and the name of the people who will work with me on the lab, because you can work in teams too, then I don't get that point, period. Okay? So it's all built in. So you could check yourself in here and see how much you're going to get. Out of the 53 points, how much you're going to get. Did I do step one? If I did, then I can give myself a point because of the fact I wrote my name and the name of the person or the people who worked with me in the lab. Since this is a small classroom, you can have 2 people in the same lab. At worst case scenario, 3. Don't have the entire class in the same lab, okay? That's not good. It's not productive. Okay, 2 people at most. So this is wrong, okay? Not January 29th. This is the instruction that need to be updated. It's actually due, it should say due September 4th at 11 p.m. That is when it's due, okay? Now, an objective include at least 2 sentences describing concepts explored and methods of exploration. What needs to be done? And it has to be at least 2 sentences or more, okay? So this, again, if I do that, please use full sentences, okay? Don't use bulleted lists, item 1, item 2, item 3. That is not accepted. You have to use full sentences. You are scientists trying to communicate your ideas in full sentences, with full grammar, with full, everything is correct, okay? I don't grade you on English, but I grade you on science. So you really have to be accurate in your descriptions. Obviously, the first one, I will give you a lot of basically feedback on it so that you know how to do the next time around, okay? So you'll get a lot of feedback. If some of the elements are in, you get 1 point, otherwise you get nothing. And so on and so forth. Every question in all of the labs is worth 2 points. Every objective in the labs is worth 3 points. This is not true for this lab. This is for all the labs. It's consistent throughout. Every time there is a name in the lab, your name, it's worth 1 point. Every time there is one formula calculation in the lab, that's worth 1 point, okay? Every time there is a question and you see a bunch of questions, 1, 2, and 3, 4, 5, those are worth 2 points each, okay? And they're graded correct answer in full sentence format with proper units when needed, 2 points. Missing some of this, 1 point. If it's completely wrong or you did not answer all of that or it's blank, you get 0 points, okay? In other words, if you follow this rubric, you should be able to grade yourself. Nobody should really grade it for you. You know exactly how much you're getting from this lab. Same thing. Tables depend on the number of cells because each cell is worth 1 point basically, okay? Partial data or wrong data will give you this partial credit. No table or no data or all of it is missing is 0 point. Same thing, there are 2 tables in here and more questions coming, and the conclusion in all of the labs is worth 5 points. The conclusion must refer to the objective and whether or not it's met and how. Furthermore, the conclusion must include data in it, especially the error analysis. How confident are you in your results? How good it is, okay? So the error analysis and numbers need to come, unless there are no numbers in the entire lab, need to be shown in here to get the full credit of 5 points. If not, you get 2 points. If not, you get 0 points. You do all of that, you get 53 points out of 53, which is 100% in this lab, okay? So this is the lab. Let me open the, are you guys looking at the same thing or did I talk lab 1? Yes?
Yes.
Okay, so let me open the lab instructions, and once I do that, let me first of all download it so that I open it in PDF, open with not Firefox, I want to open it with Acrobat. And let me stop sharing the screen in there because I'm sure that you're not looking at the same thing. Here is the lab. This is where I said the name, okay? Your name and that of the people need to go. The objective need to go in here with 2 or more sentences. Then you read the instructions, try to do everything in here. Question 1, answer in here. 2 points. Question 2, answer in here, 2 points. Question 3, answer in here, 2 points. Question 4, answer in here, 2 points. Question 5, answer in here, 2 points. Okay? The table, I don't remember how many points, but it's worth the points that we said in there. After you do all of this stuff, of course, that you're supposed to be doing. Because there is a link that you need to follow, and here is the link, okay? Once you do that, you should be able to get all of these things working, okay? There is another table, and then based on this question, 2 points. Another question, 2 points. Conclusion, 5 points. You may choose to opt out of this form completely and make your own form as you wish, like for example, on a text form or a Word document or something. But if you do so, please refer to these items in this order, okay? So that they are graded properly. This is just supposed to help you as a guide, not as a requirement. This is not a requirement. This form is not required. So if it doesn't work with you, you have to use your own. Now, here is the deal. Sometimes, depending on what type of PDF you have, PDF reader you have, you may run into difficulty that doesn't save. Do not leave it to the deadline, which is September 4th at 11 p.m. Just around 10:53 p.m., you decide to upload this file. If you do that, that is the time when the light will go out. That is the time when the internet stops working. That is the time when basically your computer shuts down for some reason. That is the time when all things go wrong, okay? Don't wait until that time. When I say 53 p.m., I didn't mean 52 p.m. either. Okay, so you have to give yourself a big window of time, at least 5-6 hours ahead of time minimum, because once it's successfully uploaded, look at it yourself. Go in there and check that it's there for sure, and open it, because sometimes these things don't save. Especially if you open it with a browser, it doesn't save. The forms do not save. So you did all of that wonderful work, and you put all of this data, and you spent a lot of time putting them together. And now, after you're done, after 3 hours working on this lab, it's not there. It's bad, isn't it? So try to save your data somewhere else. Test the file first. Write your name first and close it. Did it save it? If it's saved, it's probably safe bet it's going to save everything else. Okay? Before you start working very hard and putting all kinds of stuff in it, and then at the end turns out to be not so. Okay? So this is in a nutshell basically how the class is structured, the stuff that is coming soon, how we work in terms of participation. I'm glad that everybody is in here today. We have the entire class in here. Actually, there is another one of you guys that asked for the code, but he's not here. And he's coming from the other college, from Valley. Apparently the class was canceled there, so he's trying to transfer in here for this class. And so I'm going to still post this recording later on in the day when it's available, okay? Going to also, by requirement, I think we'll have to post also the accessibility text for it, so that to make sure that we are compliant as a college, and also to benefit the students who really need that, because sometimes actually it's better that you're sitting at home and turning off the microphone and just watching basically the caption going around in front of you, because sometimes I may say something, but the caption will be the way that it's there, because you might understand it differently, okay? So I have to post the captions, and once that's ready, I'm going to post it and the link in there. It's going to be on my YouTube channel. I have a YouTube channel where I put all of my videos, all of my working with the students. And if you subscribe to it, actually, the benefit you're going to get is that anytime a video is posted, you will be notified about it. Watch for the title of the video. It has to say PHY252 F21 for fall 21. If it doesn't say that, it's not your class. I mean, you may choose to watch it if you like, but you may not want to, because it's probably going to be an hour and a half, an hour 15 minutes, an hour 10 minutes of video that you may not want to spend that much time on it because of the fact that it's too long in there. Okay? Any questions so far?
I'm having trouble getting into the Mastering Physics with the course ID.
What does it say?
It's your last name with 11315. Oh, it says the course ID does not exist.
Okay, there is a page.
You have to click add course. So when you go into it, it's not, because mine has the book from last semester, but there's like a little blue thing that says add course. When you click that, it works. And you should have got like an email from the school with like the book, because they're giving it to everyone, the Pearson thing. And in the email, it has like how to do it, but you just copy and paste the add code from there. And once you add that book, you put in his name with the number.
She knows because she's already enrolled, okay? I was going to ask her, okay?
All right.
So we'll try to work it out. If there is still a difficulty, I would be more than happy to help you with that, okay, guys? Okay? Let me do the discussion item today, because we should not really leave without it. It's very important that you're going to go and do that. And it's actually one of the objectives of the class. So let me go back into the same OneNote that I had before, and the item that we need to discuss. So let me share the screen. And it's about the conversion from one system to the next system for the temperature. First of all, the Zeroth Law, you can put it in your own words if you like, and you can read about it in the book. Here is how it states basically. Can I do something in here? Because I'm a little bit, I want to make sure that I'm correct on this one, okay? I really don't want to give you false information. Okay, give me a second, okay? Just wanted to grab the book, okay? Yes, correct. The thing with it is, chapter 17 is exactly where we need to be. Okay, that's the thing. So, because when I asked the question about sound, I was a little bit confused, a little bit, because I didn't get any. You guys remember it from Physics 250 or not? Sound waves, waves on a string.
Yeah, I think it was.
I don't remember. It was at the end.
When you
The
did
only
the
thing
step.
I found is that we had a lab and we talked about like sound, like the energy and nothing more. I don't think we did like anything furthermore.
It was at the end of the semester, and we just like we had a lab.
We don't really need it a lot, honestly. We need probably only the wave equation at some point, which I'm sure we also did in chapter 36. Here is the wave equation. I'm just going back because I thought when I asked it earlier, it was kind of a, so this is the wave equation that you guys remember from before. So the second derivative, this is basically the disturbance. It doesn't matter what you, it could be string basically going up and down, for example, or it could be an electromagnetic wave, the X component of the electric field or the Y component of the magnetic field, doesn't matter which one we're talking about. So this is the partial derivative with respect to time. It's equal to the partial derivative with respect to time, except I need to correct the units because this is meter, this is second, meter squared, second squared. So I need the velocity squared. So this is the wave equation. Okay, this is a wave that propagates in space, but it's also time dependent. Okay, this is the right wave or the left wave. So this is from Physics 250 actually. And later on, you guys have done it. So from chapter 15, and also you have done it in chapter 36 when you saw for Maxwell's equations. Here, for Maxwell's equation, you had the electric field or the magnetic field. The electric field or the magnetic field, this was actually the speed of light, okay? This was actually mu naught epsilon naught. 1 over CB squared from physics to turn out to be the product of these two numbers, okay? The inverse is exactly the product of these two numbers, okay? So that's what you did in Physics 251. And Physics 250, from chapter 15 and 16, from chapter 15, it was, let me remember correctly, it was the tension in the string divided by the linear mass of the string. That's what I was talking about earlier, the stiffness of the medium and things like that. And this is the tension in the string that causes the wave to propagate in it. And for sound, it has to do with the bulk modulus for chapter 16, the bulk modulus, and also the density of the air. And that's why sound does not travel, for example, in vacuum. So if you are in outer space, there is no sound. You can scream your head off, and the person next to you does not hear you, even if you scream in their ear, as long as there is vacuum. So that is basically what you learned in from Physics 250 and 251 about that. So at some point, we probably are going to need this one, and we're going to need it for sure to derive Schrodinger's equation, because it's a wave equation, except that it's a complex equation, okay? That's all. So I just remembered that, and I was going to talk about chapter 17, and I was thinking this must have been covered, so that's why it should be something that we may come back to it. Okay, I know it's partial different. Did you guys do partial derivatives already in math? No? Yes? Yes? Pretty good. So this is stuff that is familiar to them. Okay, let's start with Physics 252 with the simplest thing there is, and that is the zeroth law of thermodynamics. Okay, this is my short way of writing these things. Basically, this is what the law says. I have system A, I have system B. And I have system C. Okay? What the law says is the following. If these two systems are in thermal equilibrium, what does that mean? That means if I take one system and the other one and note that there is no, the temperature between them is basically, they feel the same. One of them initially was hot, the other one was cold, but if I wait long enough and put them in contact with one another, they will exchange heat so that they reach equilibrium. That's the assumption I'm making, okay? And also in the same fashion, system B and system C are also in thermal equilibrium. So this is my F. System A is in thermal equilibrium with system B, and system B is in thermal equilibrium with the system C. Then what this Zeroth Law is saying is the following. Then system A and system C are also in thermal equilibrium. Okay, that's basically what the Zeroth Law is saying. Put it in your own words or schematically like this one, it doesn't matter. This enables me to invent something, which is a thermometer. Because this is what I'm going to do. I'm going to use water in here for system A. So I'm going to assume that this is water. And we're going to bring a device in here that I'm going to put scales on it. Okay? And see where this gas is going to expand or this liquid is going to expand when they are in thermal contact. Basically take this one and put it inside the water. When this is frozen, when it's frozen, I'm going to call this one 0 degree Celsius. When it's frozen, I'm going to call it 32 degrees Fahrenheit. Or call it 17 degrees, physics 252 preferred units of system, whatever you want to call it, okay? Who's the dean? Muse, okay? Let's call it Muse, 17 degrees Muse. Does anybody object on that? No? Okay, so whatever system you want to do, you can put it in there, okay? Hopefully he's not listening and he's going to say, how are you inventing stuff after me? He's the dean, isn't he? Ben Muse, you guys don't know your dean? For us, it's for the sciences. Anyway, so that's basically how we define a system in here. So when it boils, when it reaches the boiling point in here, so I'm going to add heat to it continuously, put it on furnace. And when it boils, this gas, because it's in thermal temperature, is going to also increase its, the heat will go into it. And I notice that the gas will expand and reach this point. I'm going to call this point 100 degrees Celsius. It's going to reach the same point in here. It did not go any point, the same point in here. So this point is actually what I'm going to call is 212 degrees Fahrenheit. And I can come up with my own system if I want to. Okay. Now take this one now, after I did all of these graduations on this system, take this one, and this I don't know what its temperature is. Remove it from the water, wait for it to cool down, and then bring it in thermal contact with this element in here, and wait for it to reach thermal equilibrium. Wait a long time. Then let's say, for example, the reading is 21 degrees Celsius. It corresponds to this point on this scale, when the water received this much heat and went from frozen to about 21 degrees Celsius on this scale. So that's what allows me to invent a thermometer. You guys understand this point? This is one of the objectives of this class, and you already met it. So how can we convert from one system to the other? Simple math. We're expecting a linear function. This is degrees Celsius. This is Fahrenheit. Okay. This is the y-axis, the independent variable. And this is this is the dependent variable, and this is my independent variable. When x is 0, this is 32. So my coordinates are 0, 32. Going to the second point in space in here, this is 100 on this scale, corresponds to 212. And the 212 Fahrenheit, of course, is the same point for the liquid. So I can plot this function y as a function of x. So 100 corresponds to 212. So it's simple math now. The slope of this graph, first of all, the y-intercept is 32. Okay? And the slope is m, because the function in here, mx plus b. M is simply equal to this y2 minus y1, 212 minus 32, divided by x2 minus x1, which is 100 minus 0, and that should be 180 divided by 100, and that should be 9/5. Okay? Simple math. Okay? Then the function b is actually equal to 32. That's the y-intercept. So the temperature, when it's measured in degrees Fahrenheit, must be equal to 9/5 times the temperature when it's measured in degree Celsius plus 32. Can use this equation to solve for the opposite to it. Can solve for x from this equation. X will be clearly equal to y minus b divided by m. In other words, and m, remember, is 9/5, so it's going to be 5/9. So the temperature in degrees Celsius is equal to 5/9 times the temperature in degree Fahrenheit minus 32. And that's it. That's how we convert these things. I know it's a simple task now for you guys to give you a temperature. The weatherman says it's a beautiful day of 73 degrees Fahrenheit. When I first heard this one, I was really scared. What is 73 degrees? I had to put it in this calculator in here to find exactly what the temperature in Celsius is. You can find it in here, okay? 73 minus 32, that is what? 41 times 9 times 5 divided by simple algebra, okay? So this is some of the objectives of this class that you need to learn. Until now, really, I'm struggling with the units for the temperature, miles, and things like that. I mean, honestly, I'm trying to be honest with you guys because I was born and raised in the metric system. This is not the full story, though. People noted that gases, and we're going to talk about this one, have this property. This is the temperature scale in degrees Celsius, okay? And this is gases that meet a specific requirement called ideal gases. Depending, so if I take the pressure, for example, depending on how much, the pressure and temperature are proportional to one another in this line, okay? From below 0 degrees Celsius to higher enough temperatures. The same gas will have a different slope, actually. A different gas, I'm sorry, will have a different slope if it meets the same requirements in terms of density and things like that. If I merge these two lines, convert them, they seem to meet at a certain point, which is negative 273 degrees, negative 273.15 degrees Celsius. That's where the pressure seems to drop to 0. And this is not true just for this gas. As a matter of fact, for other gases too, they seem to follow the same, they meet somewhere in the same point where the pressure drops to 0. So this system is really not what scientists use. They don't use a degree Celsius. They use another system, which is called the Kelvin scale. On the Kelvin scale, temperature is measured differently. In other words, the temperature in Kelvin, T Kelvin, is equal to whatever it is in Celsius, add to it 273.15. Okay? Note the notation. We use degree for Fahrenheit. We use degree for centigrade. We use degree also for, what is that? I forgot the name for it. There is another one popular also among engineers. But we don't say degree Kelvin. I mean, you might heard me. If you do, that's a typo, actually. I misspoke. It should be Kelvin, just like units for pressure, which is Pascal, or force, which is Newton, and magnetic field, which is Tesla, or whatever unit that you want to think of. But it's not really a unit. It's a scale, okay? So you need to be familiar with these conversions. This equation, the last equation, is critical for all of our calculations, okay? Unless you are dealing with a difference temperature. If you are dealing with a difference in temperature, let me go back to the share. If you are dealing with a difference in temperature, then it doesn't matter which scale you use. If you're using the Kelvin scale or using the centigrade scale, is the same thing, because the 273 will deduct it from both of them. Okay, so for delta T, whether it's in Kelvin or in centigrade, it's the same thing. And you will have a lot of equations that involve delta T in them. How much heat in an isobaric process, basically at constant pressure, it's the specific heat times the change in temperature. So in this case, it doesn't matter which unit you use. If it's an isochoric process, it's CV, the specific heat as constant volume times the difference in temperature. If it's calorimetry, we're going to do that. It's the specific heat in general times the difference in temperature. So if that's the case, then it doesn't matter. The change in energy between a system from one level to another, it's also the difference in temperature. But some other processes do not involve the change in temperature. You have to integrate over the change. Case in point is the entropy, for example. I'm going to give you quickly the example of the entropy. I know it's chapter 20. And I know some of you are saying, okay, wait a minute, why are we talking about chapter 20? We're still in chapter 17. Because I have seen this time and again from exam 1, and I really want to emphasize on this point from the get-go, okay? And you will be calculating the entropy then. So if you calculate the entropy between two different points in the cycle, and let's say, for example, this is point 1 and point 2, it's equal to dq over t. I cannot use in this expression, technically, these two expressions, they're different depending on the system that you're using. As a matter of fact, this expression blows up at when the water freezes, because if you put t equal to 0 in here, you're dividing by 0, and that is infinity. So I really cannot use the centigrade in here. I have to use the Kelvin. So I have to use the Kelvin. Okay. I mean, to be on the safe side, honestly, use the Kelvin. When in doubt, use the Kelvin. Okay? Does this make sense? Because I have seen it time and again. And no matter how many times I warn, I'm glad that I have few of you guys in here. And like last semester, where I had like 18 students in the same class, so that you guys can be easily reminded that this matters when you're doing calculations for the entropy, for the energy, for the work, for the heat, for all kinds of things. Okay? If you're dealing with a difference in temperature and the expression calls for a difference in temperature, you have a choice. I mean, between Kelvin and centigrade, you don't have a choice with somebody else, okay? So if the temperature in Fahrenheit, you have to convert to one of them to stick into SI units, okay? In general, you have to be careful. Use the Kelvin, okay? Like this expression I have shown, is going to blow up if you use if the water, if the substance goes from negative 17 degrees, for example, to 23 degrees, then there is between them a value where this expression blows up. If you put the centigrade instead of putting the correct units. So when in doubt, use the correct units. So in your discussion, you're going to write the formulas that I have discussed today. Just show me that you're on top of this subject. Sounds good? Still, I have a, oh man, it's 12:40. That's exactly our time. Unless you guys, do you guys have any other classes now or not? No? Okay, so basically from now on, when we meet, here's the plan. We're going to be discussing problems, okay? Going to be solving problems that I'm going to choose. And we're going to also discuss the piercing problems to see if there is anyone that is giving you a hard time. And we'll discuss the topics that are going to be covered throughout the week. And you guys should be able to do the reading. If you come to a section that is hard to understand or difficult, please let me know so that we're going to have that discussion. I will have recordings probably before the class for the derivations and the things that you're going to be doing so that you prepare ahead of time for the stuff that needs to be prepared, that these concepts, but then we're going to hit it right away with the problems. Because that's actually a good technique to learn how to do physics, is to actually do things. Which brings me to an important point. You have to do this thing. I know I just did stuff for you guys, but if you don't do it yourself, if you don't get your hands dirty, you're not going to be able to be confident at it. Sounds good?
Yep.
Okay, very good. So we're going to be meeting every week this time around, potentially more, okay? If you guys like to. And we're going to be discussing these things. I don't know what's the status of the physics club on campus. I know in the past, I was very much involved with it. And I know Dr. Adams took over that, and I really don't know exactly what the status, if we're going to still do that or not. But if it is, I'm hoping that you guys will join it also. I have a big event coming October 31st, because I have 4 sections of astronomy this semester with someone else, okay? And where we're going to do the James Webb launch, which is a big deal. Meanwhile, try to keep up with these things, and you will have your first homework assignment on Pearson. Your homework assignment is required, okay? So this is all the way throughout. Okay? So, but there will be chapters where we're going not to have homework, and there will be chapters that will have homework, especially the important ones, the ones where the key concepts are going to be covered and they have big implications on exams. Sounds good? Okay, so I'm going to stop the recording right now.